My name is Jessica Matthews, and I am a physical scientist at NOAA's National Centers for Environmental Information. And for those of you that might not know, NOAA is located in the United States, and it stands for the National Oceanic and Atmospheric Administration. And NCEI, the National Centers for Environmental Information that are a part of NOAA, is located in Asheville, North Carolina in the United States. I'm delighted to be here to speak to the participants at the Climate Match Academy. And I've been asked today to talk a little bit about an introductory experience to remote sensing, particularly as remote sensing can be applied to produce climate data and also apply that climate data. So I'd like to start off today talking a little bit about some basics of satellite technology. And the first thing I want to introduce is the concept of different polar orbiting versus geostationary missions. So NOAA has produced very nice videos on their YouTube channel, and I've linked one here, but you can feel free to explore the NOAA YouTube channel that may have a bunch of different videos that would be helpful as you get familiar with satellites and the remote sensing data that comes from them. So first off, this graphic is illustrating polar orbiting satellites. Then it goes into geostationary satellites. I'm going to go back a little bit to show you a little bit more about the polar orbiting satellites and how they gather information about our Earth. As the name implies, they orbit around the poles, typically about 540 miles off the surface of the Earth. And as the Earth rotates, they go around it. And you can see this striping pattern in the image. That's what we refer to as a swath. And the data that they're collecting is in that swath. But as the Earth rotates underneath of it, they continue to orbit the poles and eventually will collect data from all points around the globe. Alternatively, geostationary satellites are located much further away from the Earth's surface, approximately 22,000 miles off of the Earth's surface. And geostationary satellites will orbit at the same rate as the Earth, so they're always looking at the same piece of the Earth disk, as you can see in this animation. Just to describe a little bit more about the differences between these two types of missions, this chart kind of summarizes a little bit of maybe not so much pros, cons, but advantages of one versus the other. As you can imagine, given the position of the geostationary satellites, they really have minimal polar coverage. So if the application that you're interested in has to do with data over the poles, the geostationary platform may not be appropriate for your application. However, the polar orbiting missions actually have multiple pole crossings per day. It's the best temporally sampled piece of the Earth from the polar orbiting missions. So that might be more appropriate for your purposes if you're interested in what's going on at the North or South Pole. Given the distance of orbit, recall that the geostationary satellites are much further away from the Earth's surface. The data that's derived from them tends to have poorer spatial resolution. However, because the polar orbiters in that near-Earth orbit are much closer to the Earth's surface, they tend to have better spatial resolution. Conversely, it's the opposite for temporal resolution, which means how often we're getting data samples of a particular piece of the Earth. Because geostationary missions are always looking at the same piece of the Earth disk, they have much greater temporal resolution, sometimes on a minutely basis. Whereas because the polar orbiting missions are circling the Earth, they may only cover a certain part of the globe, maybe once a day or less frequently, depending on the particular sensor. And again, the primary difference is that geostationary satellites will view just one section of the world at a time. For instance, NOAA's geostationary satellites are primarily looking at North and South America. However, other international agencies are examining different parts of the globe with their own geostationary orbits. But polar orbiting missions will always have that global view due to the rotation of the Earth. So let's get into what about the sensors that are on these geostationary or polar orbiting platforms? What are they really measuring? And I have to admit that when I first started my career in Earth observation, I honestly thought that there was actually like thermometers that were on board these satellite missions, and that's how we were getting temperature data. Are satellites really flying thermometers though? They're not. The sensors that are on satellites tend to be things like radiometers, which measure optical radiant energy. For example, look at the figure on the left. This is an illustration of the effects of solar radiation in the Earth's atmosphere. So we have this incident solar radiation coming from our sun, and the shaded area represents the atmosphere of the Earth, where that incident solar radiation could either be scattered, absorbed by the atmosphere, or transmitted through the atmosphere down to the Earth's surface, where it could in turn be reflected. And what is the satellite getting? It is measuring that amount of radiation that's either scattered by the atmosphere or reflected from the Earth's surface through the atmosphere. And this is happening on a variety of wavelengths or channels, depending on the sensor that is on the satellite. A lot of the applications that we're familiar with operate in the visible spectrum, but different sensors focus on different parts of the electromagnetic spectrum that's illustrated on the right. Okay, so we know that they're not flying thermometers, and they're measuring some things about the incident radiance. So how do we get from measurements of incident radiation to something that we really care about, something like sea surface temperature or land cover or land temperature, or any number of other variables that can be derived from satellite information? Essentially, this is accomplished by what we can refer to as a forward model. So on the left-hand side, you can see that this is just an example from one satellite sensor called ASTER. And it has a number of channels on that sensor that measure the radiance in different parts of that electromagnetic spectrum. And we refer to those as channels. So for each of those channels, we have an array, spatially and temporally, of observations of radiance at those wavelengths. We can take that information along with other ancillary inputs illustrated here by this purple box on the bottom, things that could be topography of the Earth or carbon dioxide forcings, or any number of other ancillary inputs. Put them all together as inputs into that inverse model. And out of that inverse model comes what we refer to and what we'll use in our data applications, the final satellite data information. So there are many groups of people that focus on developing the model, or the green box as represented in this figure. So satellite data can be characterized in terms of different processing levels. What's known as level 0 data is completely unprocessed at the full resolution as captured by the satellite sensors. Level 1A goes a step further, keeps it unprocessed, but includes ancillary information such as geolocation and time referencing, as well as calibration coefficients. Level 1B data takes it another step further and processes it to sensor units. Level 2 data is the derived geophysical variables. That would be the output from our previous slide of that model. Level 3 data takes it one step further and takes those geophysical variables and maps them onto a uniform space-time grid. And finally, the highest level of processing, level 4, this includes model output or variables derived from multiple measurements. So to kind of contextualize what level data that you might be interested in working on, if you were a member of one of those teams that's working on a model that's deriving a geophysical variable from the radiance observations, you might start with level 1B data as your model input in order to get to the outcome of a level 2 derived geophysical variable. If you're just interested in applying the satellite data to answer a research question, you'll likely either be using level 2 or level 3 data. Level 4 data doesn't happen a whole lot of times because it does go through a number of processing steps to get there. But it is out there, although a little bit rarer than the level 2 and level 3 data that most people work with. So a little bit of a history lesson. Historically, satellite data was used by the weather community. They wanted to understand, is a hurricane coming? When will it get here? How fast is it traveling? And then after the event had passed, the data wasn't so useful to them anymore because they're only interested in present and future conditions. However, in recent decades, the climate community has had a much stronger interest in getting value out of what was previously data just used for weather observations. And to do that, the concept of a climate data record came about. And a climate data record is a time series of measurements that has sufficient length, consistency, and continuity to determine climate variability and change. They provide trustworthy information on how, where, and to what extent the land, oceans, atmosphere, and ice sheets are changing. So what this slide represents is the challenges that exist to actually create a climate data record from those weather observations from the satellites in our past. On the left-hand side, you'll see a figure that is a bit dated, but it resonates the concept of what I want to impart to you. So this illustrates the NOAA polar orbiting missions, the series of missions that have gone on for multiple decades. It began in the late 1970s with the TIROS-N mission. And from there, what this time series diagram illustrates is when the launches and operational time periods of subsequent satellite missions occurred, going with NOAA 6, also in the late 70s, all the way through NOAA 8, 9, 10, 11, 12, 14, 15, 16, and 17, which gets us into the 21st century. The yellow portion of the bar indicates the expected operational lifetime as depicted from the designers of the satellite sensors themselves, whereas the orange bars illustrate how long those missions were actually active and producing data of value. On the right-hand side, this really illustrates the challenge of climate data records. Space is a very unforgiving environment. There are extreme changes in temperature and conditions that impact the sensor itself. And what happens is, over time, the sensors degrade due to those harsh conditions in the space environment. So what we see on this figure on the right is what the data would say if we didn't do anything about that sensor degradation that's taking place. In that orange time series, you can see that the response, the longer the sensor has been in operation, the sensitivity of the sensor itself is degrading. This didn't matter much when satellites were being used for only weather purposes because the day-to-day changes weren't really that impactful However, when you want to repurpose this data for climate applications, over a few years, that degradation really does matter. So teams of folks have put in a lot of effort to go back and produce this consistent satellite record over time so that this satellite data can be repurposed for climate applications. And the result of their efforts is what's illustrated in the red time series on the right. You can see that if we're trying to detect climatological trends, we wouldn't be able to tease out the difference between sensor degradation and those climatological trends if using that orange uncorrected time series. So this effort is very important. As I work at NCEI and at NOAA, I am much more familiar with the climate data records program that is employed here. And as such, I'd like to offer a few of examples of the different climate data records that are available at NOAA. They're comprised of several different groupings. We have an atmospheric grouping, which would include such derived geophysical variables as aerosol optical thickness, various cloud properties, outgoing long-wave radiation, ozone information, and a lot of information about different precipitation characteristics. There's a second bucket that's focused on oceanic variables, including observations of sea ice concentration, sea surface temperatures, and ocean heat fluxes. The third bucket is comprised of terrestrial variables, things like surface reflectance, normalized difference vegetation indices, leaf area indices, the fraction of absorbed photosynthetically active radiation, or FPAR, snow cover. Additionally, we offer a fourth bucket of CDRs that are fundamental records. This can be related to the level 1B data that I referred to earlier. And the example shown here is one of the NDVI CDRs that we offer, the Normalized Difference Vegetation Index, and what that would look like in a global picture. As I mentioned, NOAA's NCEI houses NOAA's climate data record products. This facility has one of the world's largest active archives of weather data. We have more than 26,000 data sets and products, and those data amounts exceed 37 petabytes. In addition to the climate data records that I've already mentioned, there's also a lot of other environmental variables that could be of interest to you. Things like model outputs, radar observations, ground-based in situ weather station information, as well as aircraft and ship measurements. The scope of our mission reaches from the bottom of the ocean floor to the surface of the sun. So I want to offer you this information now that we've introduced what climate data records are and what some sort of satellite remote sensing climate data that's available. I want to give you the opportunity as to where you may be able to access and download that information. NOAA's NCEI is one of those options, as we provide all of our data publicly and freely available. Another place that you can access information is from NASA. NASA has what's called the Earth Observing System Data and Information System, or EOSDIS. And they use what they call DACs, or Distributed Data Active Archive Centers, to disseminate their information. The DACs are thematically organized, meaning that each DAC focuses on a different part of the Earth system. For instance, the PODAC, which is located physically out in California, contains data that has to do with things like gravity, sea surface temperature, ocean winds, and topography. Whereas the LP DAC houses information about surface reflectance, land cover, and vegetation indices. And you can see there's a number of thematically organized DACs, but all of them process, archive, document, and distribute their data from NASA's past and current Earth observing satellites and field measurement programs. So this is another place that you may access remotely sensed environmental information. EUMETSAT is another alternative data source. So EUMETSAT is based out of Darmstadt, Germany, but it's an intergovernmental organization that contains 30 member states. Their climate data access is provided by SAFs, or Satellite Application Facilities. And really, this is analogous to the NASA DAC program, where they have thematic SAFs. There's a CM SAF, which has climate monitoring information, land surface analysis SAF, or LSA SAF, as well as a number of the ones that you can see listed here to the right. International cooperation is really important as far as sharing information about our changing Earth system, which involves all of us. So this figure on the left illustrates all of the satellite missions that are currently in orbit from a number of different countries across the world. You can see in the blue highlighted region, that's the geostationary orbit that we talked about earlier. So this is the one, if you recall, that's pretty far distance away from the Earth's surface and rotates at the same speed so that it's always getting the same Earth view. But you can see that a number of countries have satellites in the geostationary orbit. So we're really getting a good picture if we all cooperate and share data amongst ourselves as to what's happening globally. The red orbits on this diagram illustrate where the polar orbiting missions are, and there's a number of those that are all listed within the geostationary orbit ring there. There are a number of groups that are trying to facilitate this coordination and make agreements between countries to share information. A few of those I've listed here on the right: the Committee on Earth Observation Satellites, the Group on Earth Observations, the Coordination Group for Meteorological Satellites, and the World Meteorological Organization. And through all of these agreements, you may be able to access additional data. So now that we've introduced what these remote sensing platforms are, how the data is generated, and where you might access it, I thought I would take a few minutes and give you an example application of how you could use climate data records. And this is a very specific example from some work that I've done with colleagues over the past few years, looking at sea ice in particular. Scientists refer to the first ice-free Arctic summer year as when the annual minimum Arctic sea ice extent is less than 1 million square kilometers. The prospect of an ice-free Arctic in our near future, due to the rapid and accelerated Arctic sea ice decline, has brought about the urgent need for reliable projections of the first ice-free Arctic summer year. To understand when that first Arctic ice-free summer year may occur, we decided to analyze the climate data record time series from sea ice concentration. We were able to take from the sea ice concentration information and determine what an annual minimum sea ice extent was and create that time series. Then we used a number of statistical models to estimate what those observed climatological trends were, and then to extrapolate those trends to predict when that first ice-free Arctic summer year would occur. The figure on the left demonstrates what we found. We were looking at different time series lengths to see how that would influence the FIASI projection would be. And when you can see, as we move towards the most recent data, which at the time of this work was 1986 to 2015, it appeared that the different statistical models that we were examining were beginning to converge and start to agree on when that first Arctic ice-free summer year may occur. In particular, those estimates using the 1986 to 2015 data suggest that the Arctic could be ice-free in summer as early as 2037, plus or minus 6 years. So that's 2031 to 2043, well within our lifetime. We wanted to take this research a step further and understand how the CMIP model suite was agreeing or not agreeing with the projections that we produced directly from the observational data. The CMIP model suite, or the Coupled Model Intercomparison Project model suite, is highly used by global decision makers to better understand past, present, and future climate change. The monthly time series of Arctic sea ice extents, as computed from NOAA's sea ice concentration CDR, was compared with 12 CMIP climate model sea ice extents under 2 different emissions scenarios. The medium scenario is referred to as RCP 4.5, and the high emissions scenario is referred to as RCP 8.5. And we wanted to evaluate and characterize how those models were simulating as compared to historical remotely sensed observations, as well as understanding how their projections were performing and comparing to each other. You can see from this figure, as we looked at the 2 scenarios, the y-axis here indicates the year that the climate models are predicting for the first Arctic ice-free summer year. The medium scenario has that out a little bit further than the high emissions scenario, which averaged to be 2042. The legend on the right-hand side illustrates the 12 Earth system models that we were looking at. And as we compare the dates that are being projected from the suite of climate models of 2054 and 2042, we concluded that the CMIP models appear to be underestimating the rate of Arctic sea ice melting, because those satellite observations suggest that sea ice depletion is actually accelerating, while these climate models generally seem to be following a linear trend. So, in summary, what I hope you have learned from today's little presentation, I hope that you've learned a little bit more about remote sensing data, the platforms that are used for this data, the importance of climate data records. Remote sensing offers a spatially complete assessment of global climate conditions, and climate data records are a carefully curated and trustworthy resource for climate analyses. We looked at one potential application example with sea ice information, but I think the potential applications of climate data records are really uncountable. And I encourage you to pursue them with your own creative ideas for applying climate data information to learn more about our Earth system. Here I've included a few references if you want more information about the application that I showed. I want to leave you with an opportunity to explore some more learning resources that I've found helpful. NASA has an applied remote sensing training program, referred to as RSAT, where you can find a lot of information for the new user to remote sensing data. What we didn't touch on much today was the format of this data, which by and large is mainly NetCDF format, which is a hierarchical data format. There are lots of tools available, both free and licensed, that you can use to open and work with NetCDF formatted files, and I've provided a listing of some of those here. And finally, if you're looking to explore some additional examples of climate monitoring from space use cases, I refer you to the following website. Thank you for your time today. I hope that you've learned a little bit about remote sensing and its application for the climate data community. And I hope you enjoy the rest of your experience at the Climate Match Academy.